Welcome to the channel. In this video, I would like to share 3 fantastic tricks for working with the rational function y equals ax plus b divided by cx plus d. I don't think it's the most popular function in the school program, but it still happens to occur. So we will learn how to sketch its graph very quickly without using any technology, and how to differentiate it and find its inverse just as fast. To do this, we will carry out a few short investigations, nothing long or complicated, so it should be both clear and interesting. Get ready. So the first thing, as I promised, is sketching the graph. Sketch the graph of, let's give a particular example, y equals 2x plus 1 divided by x minus 3. So to sketch the graph of this function, we have to answer 3 simple questions. First question is, when will the denominator be equal to 0? X minus 3 is the denominator, so we make it equal 0. X minus 3 is equal to 0. It automatically means x is equal to 3. This is going to be our vertical asymptote. Vertical asymptote. So we can start drawing the graph. Here is the y-axis. This is the x-axis. So x equals 3. Okay, I'm not going to make an accurate drawing. So this is approximately x equals 3. The second question I have to give answer to is, what if x tends to infinity? X tends to infinity. It follows that y tends to what? So when you look at this expression and make x a huge number, then you can ignore plus 1, because relative to 2 times a huge number, plus 1 is ignorable. It's a small number, so we can ignore it. And also we can ignore negative 3, because it's next to a huge number of x. So then what we're left with is 2x divided by x. It's just 2, right? It's just 2. It means y tends to 2. Yep. So if you want to give a line of reasoning quicker, so you just take the coefficients of x, 2 and 1, and divide them by each other. So ignore plus 1 and minus 3, just divide 2 by 1, the coefficients of x, the upper one by the lower one, and 2 divided by 1 is 2. So this is the horizontal asymptote. This is a horizontal asymptote. So where is 2 here? So probably it's here. Yep, it's 2. So we have 2 asymptotes for the graph. I know the general shape of this type of function. It's a rational function. So it looks like this, or it looks like this. Yeah, so it consists of 2 branches, and there are only 2 ways it can look like. Okay, so to decide how exactly it looks like, I have to choose a sample point. I think the easiest sample point I can choose is x equals 0. If I put x equals 0 into the function, then y is going to be, so x is 0, 0. What I have is 1 divided by minus 3. So in other words, y equals minus 1/3. Of course, this is the y-intercept of the graph. Let's find it on the xy plane. 0 minus 1/3 maybe it's here. Yeah. So I know my graph must pass through this point. So can it look like this? No, of course. So I know it looks like this. This is the sketch of the graph. It's pretty accurate. So if you want to be like more consistent, you can also take into account one feature of the graph. So it is symmetrical in this point, right? So it's symmetrical about the intersection of the asymptotes. So this distance must be equal to this distance. So my graph, oh my God, my graph is a little bit, yeah, so this branch must be shifted a little bit higher. So now it looks very good. Okay. So also, it's a good tone. It's a good manner to indicate the intercepts with the axis. So this is minus 1/3. And if you want to find the x-intercept, so you take your numerator of the rational function and also solve the equation very quickly. 2x plus 1 is equal to 0. So I hope your mental skills are pretty fast. So 2x plus 1 is equal to 0 when x equals minus a half. So this one is minus a half. So of course, we have to remove this part and look at the graph. Look at the graph. It's so accurate, and you can check the work by plotting it in GeoGebra or in Desmos. So I think we can have one more example. Yep. We can have one more example. Y equals, let's say, x minus 3 divided by 2x minus, I don't know, not minus 3. Okay. So let's answer the same three simple questions. First, denominator is equal to 0. So it follows that x equals 3 over 2, and it gives us a vertical asymptote. So I can start plotting the graph right now. X equals 3 over 2. It's somewhere here, like that. Oh, let's make the graph even more interesting by putting negative sign in front of x here. Yeah, it will be fantastic. So 3 over 2 is the vertical asymptote. So the second question I asked myself is the ratio of the x coefficients, the upper one by the lower one. So it's minus 1x, of course, there. So minus 1 divided by 2. So the upper x coefficient was divided by the lower x coefficient, minus 1 divided by 2. This is y. This is horizontal asymptote. Horizontal asymptote. So y equals negative a half. It's somewhere here, I think. Yep. So this is minus a half. Don't forget to indicate the points. 3 over 2 looks like this. X-axis, y-axis. And then now I understand my graph looks like this. Yeah, two branches of the hyperbola. Or it looks, no, it looks like this. So I have to decide which position is correct. So in order to do so, I choose a sample point. It's x equals 0. It means y is going to be, so these two terms disappear because they're zeros. So the ratio of the free or constant terms, minus 3 divided by minus 3, it's 1. So y equals 1. So this is the so-called y-intercept. So let's use the red color. So x equals 0, y equals 1. It's somewhere here, I think. So of course, it means my graph cannot look like this because it must pass through the point I just found, 0, 1. So it looks like this. This is an asymptote. It's not the x-axis, so don't confuse them. And on the same distance, yeah, in the same distance, So the two branches of the hyperbola must be symmetrical in the point of intersection of the symptoms. So this is one. So if you want to find this point, as I said, the numerator of the rational function must be equal to 0 at that point. So x equals -3. So it looks like this. So don't forget to check your work whenever it's possible, using technologies, using graphing utilities. So it will make your experience richer. Okay, so this is how the graph of the rational function can be drawn very quickly. And let's consider the derivative, right? So y equals ax plus b divided by cx plus d. It's a rational function. And what if I'm asked to differentiate it? Of course, I have a function in the numerator. I have a function of x in the denominator. That's why in order to differentiate, that is to find dy over dx, I can apply the quotient rule. U over v differentiated is u prime v minus uv prime divided by v squared. Yeah. So u is the upper function, v is the lower function. So we just apply the common rule to the general form of the rational function. Okay, so u prime, look at this, it's a linear function. Its derivative is a. We multiply by v, cx plus d, minus u is ax plus b, but multiplied by v prime, which is c. Then you divide by the square of the denominator, cx plus d, everything squared. So the most interesting stuff happens when you open the brackets and combine like terms. Okay, let's do it. ACX plus AD minus ACX minus BC. Of course, X terms disappear right away. This is what I noticed when I was a schoolboy. I differentiated a couple of rational functions and I noticed that X term disappears in the numerator. So first time you differentiate, you think that it's just a coincidence, yeah? It's just it was occasional. But when you differentiate the second time, the third time, and you see the same picture, you have to be attentive enough to notice things like that. And then I asked myself, is it a general rule that x disappears? And then I made a decision to check it. And how can you check this? Of course, by doing the differentiation in a common form. So I chose ax plus b divided by cx plus d rather than a particular function. So the denominator then, so there is no need to open the brackets, to open this square, because in this form it looks more compact. So AD minus BC divided by CX plus D squared. Yep. But the most brilliant stuff about this rule is that AD minus BC can be easily found from the original notation of the rational function. Look at that. It's a cross method. Yep. So A times D minus B times C. If you're familiar with the determinant, the concept of determinant for a matrix, then of course it will be so familiar for you. But if you're not, so just skip it. So AD, so you multiply A and D minus B times C. That's it. So let's consider a particular example. Y equals 5x minus 1 divided by 3x plus 7, I don't know. So dy over dx is equal to, so I know what happens to the denominator. It must be squared, no problem. And then let's apply the rule. So 5 times 7, 35. Let's do it mentally. So 5 times 7, 35. Minus, there is a negative sign. It goes by the formula. But here, minus 1 is multiplied by 3. So 35 minus 3. So 38. That's it. So you can see how fast it is. One more example, y equals, let's have a little bit non-standard example. So 3x divided by, let's say, minus x plus 3, so something like this. So of course, you can compare with the general form of the rational function, b is 0. Yep. For this particular example, b is equal to 0. So dy over dx is equal to the denominator, whatever it is, must be squared. And then you can imagine 0 here. If you feel uncomfortable with this, you can write plus 0. Yeah, but when you're more experienced, of course, you do not do so. So apply the cross rule. So 3 times 3 minus 0 times minus 1. So it's, of course, it's 9. That's it. That's it. So the differentiation isn't a problem anymore. Yeah, so you can impress the girls, the teachers, like boys around you. So use it, please. But we haven't finished yet. The trick number 3 is about inverse function. Yeah, it's a specific topic, I know, but all the problems we have on the test, they're all specific. So y equals, again, ax plus b divided by cx plus d. The problem is to find the inverse function of the rational function given. I have to remind you the two-step procedure of finding the inverse. The first step, you switch y and x. So wherever you wrote y, you write x. And wherever you wrote x, you start writing y. Yep. So you just interchange them, cy plus d, like this. This is the first step. The second step is to isolate the value of y, or that is, express the value of y in terms of x. Yes, it's a long procedure here. So first, I multiply by cy plus d. Both sides of this equation are multiplied by cy plus d. So x times cy plus d is equal to a y plus b. Okay, I open the brackets, so it's cxy plus dx is equal to a y plus b. I remember my goal. It is to make y the subject of the formula. So I collect all y terms on the left-hand side, and I throw all other terms to the right. So it's cxy minus ay is equal to minus dx plus b. Yep, so I hope you're attentive enough. So y can be taken out here as a common factor. Cx minus a is equal to minus dx plus b. Okay, so the last operation is to get rid of the coefficient of y. So I divide both sides by cx minus a. So y is equal to minus dx plus b divided by cx minus a. So this is inverse function, so f inverse of x. So the original function was the direct function. It was f of x. So let's highlight it. Yep, it was the original function of f of x. And what I found right now is inverse function. And let's compare them. So it was ax plus b divided by cx plus d. And now it is minus dx plus b divided by cx minus a. Look at the value of b. No, it stays the same at the same place. Look at cx. It also didn't change. What happened to a? It moved here, but also it changed its sign to opposite. Yeah, it was a, but when it comes to the inverse function, it's minus a. Yeah, magic. So d also, it goes to the place of a, but it became minus d. So minus, oh, we can make a diagram like this. So yeah, a goes to the place of d by changing its sign. D goes to the place of a by changing its sign. But b and c, so they are unchanged. Okay, this is a simple rule you have to memorize. Okay, we can consider a couple of examples. Y equals, let's say, 3x minus 5 divided by x minus 2. So the inverse is, so minus 2 goes here by changing its sign to opposite. So it's 2x minus 5. X minus because this is positive 3. This is positive 3. But when it goes here, it becomes minus 3. Yeah, like this. It's very easy and very fast. So it's example number 1. Example number 2, y equals, let's say it's minus 5x plus 2 divided by x plus 1, say. The inverse is equal to, so plus 1 goes here as minus 1. So it's minus x plus 2. So plus, yeah, minus 5 goes here as plus 5. Yeah, it's x plus 5 now. Yeah, yep, very fast and easy. But before you come to the results like this, you have to make this little investigation. So my main goal here in this video is to show you the investigation, to show you how I like came to the result. I solved maybe 3 or 4 problems like this, and I found a pattern. Yep. So I found a pattern that something, so I looked at this function I started with, and I looked at the inverse function. I noticed that this minus 5, it doesn't change. And I thought, of course, the final result is related to the given function somehow, but I wasn't sure how exactly it's related to the original function. That's why I made a decision. The only right decision is to like perform this little investigation. When you want to perform the investigation, you have to perform it in a general form. Yep. So you write ax plus b divided by cx plus d. Yep. And you solve the problem in a common form. And when you reach the result, then of course you compare it with the original function. So this is how we reason. I hope the video was useful for you. So give me a like, comment the video. So see you in the next video. Bye bye.